Hello. Now we discuss the espresso algorithm. So what does espresso do? It's a heuristic strategy. It starts with an initial cover which is provided by the designer. So initial cover over the set of product terms, which over the set of min terms, over the set of implicants, right? And with this initial cover, it is a cover because it covers at all the one terms in the function, right? All the one product terms in the function is somehow covered by this initial cover. So provided by designer or extracted from hardware language model, right? Then we modify the cover under consideration. How do we do it? We do it essentially through a series of expansions to form prime implicants and then cover the set of ones minimally, right, and find a minimal cover from the prime implicants that we have found. Then we do reduction and then again expand in another direction. So this is the basic principle which is followed in the espresso algorithm. So given an expression, it tries to see which terms can be reduced literally, and reduce literally means we can reduce the number of literals in it to form primes, and then we determine its cover, reduce it and expand it expand in another direction. This is repeated until a suitable solution is reached. So basically what do? We make it prime. By expanding, we make it prime and irredundant. That means then we find all the prime implicants and then we discard all the redundant prime implicants. We find a cover over primes which is not redundant, meaning that if we remove another prime implicant, it will uncover some of the ones not being covered by any other prime implicant, right? So this is an irredundant cover. After expanding all the ones to the prime implicants, we obtain an irredundant cover over the function, and we then perturb the solution by this reduction step. This is a solution using a set of prime implicants which cannot be further reduced, because if we had expanded in this way, then it cannot be further reduced. So therefore, to now obtain a better solution, what do we do is to perturb the solution through a set of reductions. We will talk about all these steps in detail, and then reiterate until a small irredundant cover is obtained. So we often obtain good solutions. However, the solution in most cases will not be optimal. This is a heuristic methodology, and typically the size of the cover reduces and we over time, and we obtain a limited size cover. Now before discussing the espresso algorithm in detail, we need to understand how is the function represented in the espresso algorithm. So it is represented inside a computer using a data structure whose abstract representation I will present here. So the min terms in the function are represented on the vertices of a hypercube, right? For example, here this is a min term, this is another min term, this is another min term. So this is a 3 variable function, and all these min terms, all the 8 min terms have been represented on the vertices of a hypercube. Here this is a cube, 3-dimensional. Every edge connecting two vertices, for example this edge here, every edge connecting two vertices change in only one bit position between adjacent min terms. So this one is a min term here, this one is a min term here. This min term is 0, 0, 0, this min term is 0, 0, 1. So it has changed in only one position, the LSB position. Similarly, if you see this one is 0, 0, 0, this one is 1, 0, 0. It has again changed in only one position. So adjacent min terms which are connected by an edge on the cube always change by 1. bit position, always change in 1 bit position. Now, from the 3 variable representation, how do we represent 4 variables? For 4 variables, we first obtain 3 variable hypercubes. These are 2 same 3 variable hypercubes, and then we make connections accordingly. For example, this is a connection. So, between this and this, we see that only the MSB changes, right? In all other respects, this 3 variable hypercube and this 3 variable hypercube is same. For 5 variables, we duplicate this whole structure together. We duplicate this and again make connections accordingly. Now, before looking at the espresso algorithm in detail, we first go and look at each of its function. So, we said that most important steps in the espresso algorithm is a loop which goes on reducing, expanding and getting an irredundant cover. This happens over and over again until the cost is stabilized. So, these 3 functions, expand, reduce and irredundant, these are the 3 most important functions in the espresso algorithm, and therefore, we need to discuss these functions first before understanding the entire algorithm in detail. So, what does the expand function do? Expand function takes as input f and r, where f represents the current cover over implicants that we have to get the onset of the function, and we also have r, the set of don't cares. What does expand try to do? It tries to expand the cubes in f. So, we said that initially we have some random initial cover. From this random initial cover, so this random initial cover will consist of a set of cubes, will consist of a set of coverings which we call cubes or subcubes from the entire cube representation that we have. So, it tries to expand the cubes in F with neighboring cubes and with nodes in the DC set to form larger cubes. So, what does it try to do? It expands cubes in F. So, it takes one cube in F and tries to expand in a certain direction until no further expansion is possible. And how can it expand? By using either one terms or don't care terms in a given direction. So, when no further expansion on one direction is possible, then it will try to expand in another direction. Now, how does it try to expand? It takes essential subcubes and tries to expand them till they become prime subcubes. What are essential subcubes? An essential subcube is a cube containing a minterm covered by no other cube. It takes an essential subcube in F and expands it until it is prime. This is what we said. A prime cube is a cube which is fully expanded against the offset and cannot be expanded further. If we further try to expand the prime cube by reducing one more literal say in it, then it will cover some part of the offset. Okay? So, therefore, it cannot be expanded. As an example, let us say this was an initial cube in F. This was an initial cube in F. And these are two don't cares. Okay? These are two don't cares. Then we can expand in this direction, and finally we can obtain this cube after expansion. Okay? This cube will be obtained after expansion. And we cannot expand it further because let us say in the vicinity we have zeros. Somewhere we have zeros, and hence we cannot expand this further. Now, by this we can reduce the number of literals in the cube by 1. Okay? So, this is the objective. Now, implicants covered by an expanded implicant are removed from further consideration. Now, we have already removed, then it is removed from further consideration. Expansion reduces the number of terms in the expression. Okay? This is how what we said, it reduces the number of terms in the expression. Why? Because we are taking two or more product terms and combining them into a single product term. that is why it reduces the number of terms. R is required, that is the don't care set is required, so that the function knows which nodes are in the offset, and which cannot be expanded against, because we cannot cover the offset, right, while expansion. The quality of the result depends on the order of implicant expansion. This is also an important point. Suppose we have a cube. If we expand in direction x, it may give me a much bigger cube than if we expand in a direction y. So therefore there are loops in this expand irredundant reduce. This loop tries to expand cubes in different directions and try to obtain a minimal cover over primes, right, over essential primes. Now heuristic methods are determined to determine this order. Heuristic methods are applied to determine this order, in which order should the implicants be expanded and also in which direction, right. After this expansion step, we arrive at the irredundant step. What does the irredundant step do? It determines the minimal set of irredundant cubes covering the onset. Now we have already expanded using a set of primes, but all primes may not be essential. A few of the primes will be redundant. What do we mean by that? All the ones in that prime cube is covered by some other cubes. There is not at least there is not even one within this prime cover that is not covered by any other prime cube, and hence this is redundant. Next we come to the reduce step. So after we have done the expansion and the irredundant steps, the solution is usually pretty good. But as we said, if we had expanded possibly in a different direction, and the order in which we had decided to expand the implicants, the order of the implicants chosen also determine the quality of the cover that we get. And hence often after we have obtained one round and we have obtained one solution, the solution can still be made better. Okay. There might exist another cover with fewer minterms and fewer literals. This is what we said. So what do? We shrink prime implicants to the smallest size that still covers the onset. Okay. We shrink prime implicants to the smallest size that still. So then now these prime implicants will not anymore remain prime, because we are shrinking it. However, while shrinking, we are keeping into consideration that we will not uncover anybody in the onset. We will still keep a cover of everybody in the onset. We can reduce the primes, but while reducing the primes, suppose in this example I had this cover here and it was a prime cover. Now when I reduce it, we still see that here was a cover, because these are don't cares, this is still a cover. Okay. However, let us say this one is also an on. This is not a DC variable as is this one. Now when this was a cover, then if I reduce it to this, then this will not be this on vertex will not be covered anymore. If this on vertex is not covered by another prime implicant from somewhere else, like this one, say. Let us say you have on another side you have another cover for this onset. For this vertex on the onset, you don't have another cover. Then if you reduce it and reduce it to only these two vertices, you cover only these two vertices and you uncover this, then what happens? It will completely not be covered by any other prime implicant, and this is not allowed. So we shrink prime implicants. So what we say is that we shrink prime implicants to the smallest size that still covers the onset. This allows the newly formed cube to expand in a direction different from the larger cube from which it was obtained. Now, after I have reduced this, I can now possibly expand in a different direction. To allow this, I do the reduction step. Thus, new larger cubes can possibly be obtained by exploring in the new directions. The don't cares, why have we used the don't cares? Don't cares are required to know which nodes in the cube are don't care and can be dropped without the least risk of losing the cover while reducing that cube. For example, here we had two don't cares, and therefore we could reduce the cover to this. However, we said that if this was not a don't care and it was also not covered by any other prime implicant, then we could not have done this reduction in this way. Right? This is what the reduction step is. Now, after we have done the reduce, expand, irredundant steps for a certain number of times. So after reduction, we will do again an expansion, again obtain an irredundant cover, again reduce, and again possibly expand in another different direction. After this, and all the while we are doing this, we are keeping the best solution that is obtained till now. The minimum cover that is obtained till now, the best solution is always kept. So until the cost stabilizes, we will go on doing it. After this is done, we will take a simulated annealing like approach, perturb the solution completely, and try to go to a different part of the state space and again try to do this reduce, expand, irredundant step in that part of the state space. Now, how do we do that perturbation of the current solution? We do it using reduce gasp and expand gasp. So first we understand the reduce gasp. So for each cube in F, add those subcubes in F that are not covered by other cubes. So what do we have in F? As you said, the current solution is present in F. The current solution is present in F. Now the current solution is a current set of implicants which cover the onset of the function. Now we take that solution, the current solution, and then add those subcubes in F that are not covered by other cubes. For example, here we have for each cube in F, add those subcubes in F that are not covered in other cubes. So what do we do? Here we have two covers and both of them are in F. Okay. Then we add this one. This one is not, so this one is a node. This one is a node that is covered by both the cubes, this cube and this cube. However, this cube and this cube is only covered by one subcube, right? So we add this cube and this cube to F. So for each cube in F, add those subcubes that in F that are not covered by other subcubes. So we are saying that this cube, this vertex is covered by cube this and cube this. However, this vertex or this implicant is not covered by any other cover in F, any other implicant in F, and therefore we add this to F. This is what GASP does. It uses D to ensure that these new cubes are not produced for just some don't care nodes. The new cube that we form, that we add, should not consist of only don't care nodes. Then we come to the last step, the expand gasp. This function takes as input the set G produced after reduce gasp and R. So this function takes as input what reduced gas has produced me. So now in F we have many other subcubes, right? We have many other subcubes which have been obtained after this reduction and addition of cubes that are not covered by other cubes, right? Now we expand from all the cubes and adds them if they cover other cubes. So R is used to ensure that nodes in the offset are not included, right? The redundant cubes introduced are removed later. So these are the basic functions of the espresso algorithm, and we will now take a look at the detailed algorithm once more. As we said, the algorithm takes a given expression in binary variables as input and represents it in the form of a hypercube. The onset represents the nodes representing minterms which are 1 when the expression is 1. The offset represents the nodes representing minterms which are 0 when the expression is 1. The DC set consists of nodes representing the minterms which are don't care values. Initially, the cubes in the onset consist of individual nodes in the onset. The algorithm begins by expanding the onset against the offset. So this is where the algorithm begins. It begins by expanding the onset against the offset. The cubes are expanded by adding neighboring onset nodes or DC nodes. This is what expand does. The cubes are expanded by adding neighboring onset nodes or DC nodes. Once a direction of expansion is chosen, then it is fixed and the cube can expand further only in that direction. This is what expand does. So it keeps the direction of expansion fixed. When you cannot expand in that direction anymore to obtain a prime, you say that it's to expand in that direction anymore, you obtain a prime implicant, right? Once all cubes have been maximally expanded, the irredundant method is applied. So once this expansion step is done, once all cube has been maximally expanded, we apply the irredundant step. Okay, it chooses the essential cubes only, those covering nodes not covered by other nodes. It then removes those cubes, all of whose ones are covered by some other prime implicant. It removes all those nodes. This is what the irredundant step does. Of the remaining cubes, those are chosen which result in a minimal cover. Next, the reduce expression is applied. It shrinks larger cubes. So after this irredundant, we go inside this loop. We apply the reduce. So what does reduce do? It shrinks larger cubes into smaller ones wherever possible. The resulting new subcubes can then be expanded in a direction different from which they were expanded previously, and this possibly will give me a better solution. This lets different minterms to be combined to produce possibly larger cubes. So when we expand in a different direction, we will possibly get different prime implicants covering a different set of minterms, and this prime implicant could be larger than the previous prime implicant that we get. So why do we need to do all these steps? Because finally we want to get a set of prime implicants which covers all the onset of the function, and this cover is minimal in the sense it contains the minimum number of prime implicants in it. This is what is done. If a cube cannot be expanded in a new direction, then it is re-expanded in the previous direction. The irredundant cubes are then removed. This cycle of reduce, expand, remove redundant is repeated till the cost is stable. That is, the expression cannot be further reduced. Next, a simulated annealing type approach, as we discussed, is applied. The intermediate solution is perturbed by adding new cubes. These are subcubes of existing cubes, right? These are subcubes of existing cubes which are not covered by other cubes. This is what reduced gasp does. The new set is then expanded. Then the redundant cubes of the union of the new set and the intermediate solution are removed. This is what happens in this step. This new set is subjected to the same reduce, expand, redundant iterations. This goes on. The above procedure is repeated for some predetermined time, right? So this whole thing is repeated for some predetermined time until time is up to get a final solution. So espresso is an anytime solution, is called an anytime solution because the algorithm that we get can be stopped at any time and we will get a solution. So the more time we give to the algorithm, the solution is expected to be better and better, but at any point in time if we stop, we will get a solution. Hence it's an anytime solution. Okay. So a new solution can be obtained by perturbation of an old solution. We can repeat the above process while maintaining the best solution we obtained. So at any point in time, we always keep the best solution, so that at the end of the whole process, after all the iterations that we have done, we ultimately get the final best solution, the final best covering, and the minimum logic expression. So this is was an overview of a heuristic methodology for two-level logic minimization. This is a standard tool that is used in current VLSI design, and with this we have taken a brief look at the logic synthesis step in the VLSI design process. We come to the end of this module with this discussion.